University. Anyway, as I mentioned, we will start uh, new chapter, the queuing theory. Some of the students from section 2 was actually or are actually asking or requesting for a class that will completely deal with solving problems. Is it necessary for this section as well?
Yes, sir. Also, sir, can you provide us some practice problems before meet,
No.
like after we are
Practice
done?
problem. Practice problem has its own problem. A student thinks that the question will be set based on only those questions. Some students. That's why
Um,
actually practice giving practice problem. Previously, I actually provided homeworks or whatever you say. Since you do not respond, you just want to see how the question will be. Then you see the previous year's questions, and there are many questions in the exercises. But even then, I will try, if possible, to provide some problems if there is any. So let us begin with the queuing theory. Before mid, it will be the final chapter, hopefully, inshallah, and we will be able to finish it. Uh, queuing theory, actually, I will try to upload a note, and you can follow the textbook. The textbook chapter 7 is totally dedicated for queuing theory. However, we will not cover all the topics from that chapter. Just we'll try to cover some fundamental things from this chapter. What is our objective? Our objective is very clear here. We will try to understand the Markovian queuing system. There are different queuing systems. I will define it just in the next slide or next to next slide. And our study will only be focusing on the steady state analysis of SAS queuing systems. By the term steady state, as you already know, we mean that the long-term behavior of the queuing system. Most of the cases, our analysis will be focusing on average amount of time that a customer spend in the queue, average number of customers available in the queue, or average number of customer in the system, average time spent in the system. So this sort of things. Also, we'll try to cover some cases, the probability distributions of the waiting time or the service times. Not service time distribution will be given system times. So two things are our object focus. One is we will only focusing on queuing systems that are Markovian in nature. We will define what it is. And for SAS queues, we will be focusing on the steady state analysis, just the long-term behavior of the queues. So before going to the Markovian queues, let us consider what is a queue. As all of you know, it's a waiting line of customers, jobs, and items. In our day-to-day life, we encounter queues almost everywhere. If you go to a bank, there is a queue. If you go to a shopping mall while paying your bills, you need to wait in a queue. Then, from computer systems perspective, when you design routers, we need a buffer. This buffer actually is a queue where packets that are waiting to be processed or waiting to be forwarded are kept. So that's router's buffer is a queue there. And there are actually many applications of queuing systems in computer science. So this is an important properties from two perspectives. You want to mathematically analyze computing systems that has a queue, and you want to understand the performance of such queues. Then you need to actually do this one. And second thing is that when we design system, in many cases we cannot implement it, and mathematical analysis actually helps us to understand the ultimate behavior of the system. So queuing system is necessary there as well. So if we consider some of the examples, one is the router's buffer. and any line where people waits, customer waits. Now let us move on to the main topic, Markovian queuing system. In a queuing system, mainly customers will arrive take a service and leave. So when we define Markovian queuing system, we define it on the perspectives of customers' arrival nature and its service nature. We say queuing system, a Markovian queuing system, if customers' arrival follow the Poisson process, and the service time is exponential. You know, both of these are identical. When actually arrival follows the Poisson process, inter-arrival time is exponential. And when the service is exponential, you can consider the departure rate actually follows the Poisson process. So both of these customers' arrival process and the service process are memoryless and Markovian. That's why when we define a Markovian queuing system, we say that it is actually categorized based on the arrival process and the service time distribution. If both are defined in this way, that the arrival process is Poisson, service time is exponential, then the queuing system is Markovian. This is the first condition. The second condition says, if either one of these are, either the arrival process is Poisson or the service time distribution is exponential, then it is. So when an AND relation exists, then it is Markovian. When OR relation exists, it is also Markovian. So we can say in a single word, if the arrival process is Poisson and or the service time is exponential, then the queuing system will be Markovian. Primarily, our focus will be on systems where both the conditions are satisfied. So we will go for the AND relation. However, in the end, we will learn one queuing system where the service time is not Markovian. The service time will be from a general distribution. And when we will classify the queuing systems, then we will find that such a queuing system actually is denoted by MG1, where the arrival is Poisson process or has the memoryless properties or the Markovian properties, but the service time is from a general distribution. Any distribution can be used here. Under that circumstance, the queuing system actually sometimes you can say it is a semi-Markovian process, but according to the definition, if either of these two are satisfied, that means the arrival process is Poisson. Here it is satisfied. The service time is not exponential. However, due to the OR condition, this MG1 queuing system is also a Markovian queuing system. So most of the queuing system that we will analyze in the today and the next two classes will be Markovian with the condition that both of these two conditions are satisfied. On the other hand, maybe in the last class, we will see MG1 queuing system where the service time is not exponential. If you have any questions anytime, please ask. Since I cannot see any of you, it is really difficult to identify whether you are here or not, even you are listening me or not. But if you have any questions, just ask me. So first we will identify the components of a queuing system. The diagram clearly specifies the components, but let us write. Actually, in a queuing system, you need three things. 1, 2, and 3. What are these? First you need a population. From this population, customer, jobs, task will arrive in the system. Usually, we call such a system a service facility, a shopping mall, a router, a community center, whatever, a bank, a post office. So population will arrive to this service facility. Then what we need? We need a server. Number 3. If the server is busy, as we mentioned earlier, then people's customers, jobs have to be waiting. Then we need a queue. These three components now have two properties. The population actually is defined by two things. Its size. You can have a population with infinite size, or you can have a population with a finite size. And second thing is that from the population, actually we define at what rate customer will be arriving in the service facility. So we need a process here. We call it the arrival process. The population defines the arrival process. You can have a population where the inter-arrival time is, say, binomial, normally distributed. Okay, so this arrival process here is important, as we already mentioned that the queuing system will be Markovian. So most of the cases, in fact, in all cases, the queuing systems that we will be considering here, the arrival process will be a Gaussian process. And we are familiar with that. Now, the queue itself will, like the population, have a size. It can be infinite in capacity, as many customers available, whatever the size is, the queue can accommodate infinite capacity. And we will have a queuing discipline. All of you are familiar with different queuing disciplines. The simplest one is first come, first serve. You can have a priority queuing and many others. Shortest job fast, and so on. For this course, for this chapter, for simplicity, always we will be focusing on queuing discipline, that is first come, first serve, just to keep the analysis simpler. If anyone needs a different type of analysis for a different type of queuing discipline, you can search text and other resources. Our focus will be, and so the questions in the exam will be considering first come, first serve. Then we need servers. There can be one or more server. At least one. We can have more. And associated with each server, what we have, a service time. And the distribution of the service time will be available. If there are more servers, that means more than one server, then we will assume that service time of all the servers are identical for simplicity. Whenever we will be considering that all the servers are identical. So if we now focus here, then this population is here. Most of the cases we will be considering that the population has infinite capacity, infinite size, And if it has infinite size, then our queuing discipline will ignore it. We'll assume, okay. Unless otherwise specified, we will assume the queuing system has an infinite population. But when it is specified, then we'll consider, okay, it has a finite population. And then from the population, we will have the arrivals, and all the queues that we will be considering will have Gaussian distribution. The queue can have an infinite capacity or a finite capacity. Many of the cases we will consider queue has infinite capacity. Then the servers, if there are more than one, we will consider they are identical. We will start with the queuing system that we call the single server queuing system. There will be only single queue like one, but we will also consider cases where there are multiple queues. Then based on the servers, we'll have a departure process. We'll consider, unless otherwise specified, it is exponential. It has exponential service times. Any questions here?
Sir, I have one question.
Please.
Sir, what is the necessity of the population size here? Like if we entirely focus on the key.
No. Population size has actually uh, most of the cases we will be considering that the systems actually have infinite population. If it has a finite population, then actually it has one implication. It will contradict with our initial objective that we will be considering the steady state analysis, right? Unless you have a sufficient number of population there, even before you reach to the steady state, the system might actually be shut down, right? Stop. That's why the population size has impact. How many customers will arrive? This has impact. And for our case, since our study is infinite, to keep it in the safe side, we will be assuming that we have an infinite population. Is it clear now?
Yes, sir. Thank you.
Any other? Any other questions? Okay. Now, usually a queuing system is represented by a schematic diagram that we can call the queuing process. The previous one was a diagram that actually specifies the components of the queuing system, but the current one, actually, it is more representative. Always in a queuing system, we will be representing a server as a circle. So this circle will be a server. A rectangular box with one end open, most of the cases, will be considered as a queue. And if the rectangular does not have the open end, then we'll consider it's a queue with finite capacity. And one arrow actually will be pointing the arrival process. Now, whenever we write lambda here, then we say the arrival process is Poisson with red lambda. The right side arrow just started from the circle. When you write mu here, it will say that the service time is exponentially distributed with rate or with average 1 over mu. And a number of variables are associated here. And our job will be to identify the long-term steady state values of these variables, actually random variables. Most of the cases, actually, we will be calculating the expected values of such random variables. Now, what are the variables here? The first one that you can see here, the number of customers waiting in the queue and the number of customers in the service. So in sub S will represent the number of job or customer task in service. If there is only single server, in sub S can be either 0 or 1. On the other hand, N sub Q will be the number of waiting customers. One point that we will be considering here, the work conservation rule. as long as there are customer, servers cannot be idle. So it is not possible that n sub q is greater than 0, but the server is idle. The server will always be busy if there is at least a single customer in the queue. And we will have a variable n, that the total number of jobs, customers in the system, which simply is the sum of n sub q plus n sub s. So these three variables actually relates number of customers, number of jobs in the system, where it is and where they are. In contrast, if we consider the time variables, then we have w, the waiting time in the queue, x, service time, the actual time that a customer job requires to complete his or her service, and the total time. Total time sometimes is called the system time. In many books, you will find, as I mentioned earlier, sojourn time. And these three variables are connected. T is equal to W plus X. So as I mentioned before, if we summarize here, then what will happen when a customer will arrive? He or she will first look for an idle server. If there is any, then service will start immediately. There is no delay. So W equal to 0 for such customers. If the arriving customer finds at least one server is idle, the service will start immediately. On the other hand, if an arriving customer finds the server or servers are busy, then we'll join in a queue. The queue will have infinite or finite capacity. And our objective actually will be to find out the expected values of all 6 random variables. So the random variables are, as we already mentioned, n sub q, number of customers in the queue, n sub s, number of customers that are currently receiving service, n is the total of these two, and w is the waiting time, x is the service time, and t is the total time. All 6 are random variables. Most of the cases will not be actually identify or derive the equations for the distributions of all those random variables, but just to learn, we will be actually deriving the distribution of t, and once you have t, you can calculate derive the distribution of w as well, and the distribution of x is available. It will be given. So the component of the queuing system, as we have already mentioned, you will find it in the text: population, it will come with population size, arrival pattern, just to repeat it, arrival pattern, the arrival process. Then we have the service time distribution. Then we have queue capacity. Number of servers. How many? 1, 2, 3, 4, 5. Actually, you will have 6. Another one is queuing discipline. When we actually study or we have a queuing system, actually all the queuing systems are denoted by a particular notation known as the candle notation or candles notation. The candles notation has 6 components. Based on these 6 component of the queuing system, usually you will find characters M, Z, D different, but to specify this, let us consider the characters are A, B in capital, C small, D, E, F. Then let us identify the meaning of each of the characters and what do they represent. The first one, A, is the arrival process. As we already described, and the arrival process can be Poisson, or you can specify its inter-arrival time distribution. It can be taken from a general distribution. So we can have, when it is Poisson, usually we use the character M because it is memoryless. Inter-arrival times are memoryless, so we can use M. Sometimes people use a Poisson process is also a Markov process, so character M is used. You can have a general distribution there, other distribution as well. Then B is the service time distribution, which, as we already mentioned, that when it is exponential, it is also Markovian. So we can have a M/M for a Markovian queuing system. Also, you can have M/G. This is also Markovian because it satisfies one condition that either the arrival should be Poisson or the service time is exponential, or both to be a Markovian queuing system. So both MM and MG are Markovian queuing system. The third one, small c, in many books you will find it is represented as M or C. Both are okay. It is the number of servers in the system. So if we consider a simple queuing system where there is a single server, then we'll have MM1 or MG1. And if you do not mention the other terms, as I mentioned already, for example, the D represents the system capacity. If you do not mention it, then it represents the capacity is infinite. E represent the population size. Unless otherwise it is necessary to mention, we consider that it is infinite. So we usually do not mention E at all. And then we have the final character F. So, okay, let me write. D represents the system capacity. Don't actually misjudge it with the queue length. Usually system capacity represents the total number of customers that can be accommodated in the system. So when we say the system capacity is K, this represents K customer can be at most accommodated in the system. So if you have a single server, 1 will be in service, 49 will be in queue. So queue size is 49. If there are 5 servers, 5 will be in service and 45 will be in the queue. The queue size will be then 45. So system capacity represents total number of jobs or customers that can be accommodated in the system. E represent population size, and as we mentioned, it will be infinite always. And finally, F represents queuing discipline. If you do not mention it, we will assume it is first come, first serve. So, as we mentioned, we will be considering that the queuing discipline is first come, first serve all the times. We will never use F. The population size is always will be infinite, so we do not need to use it. So the last two terms here, we will consider that they have their default values. For E, it is infinite. For F, it is FC. And now D, if you mention it, then that will be the maximum system capacity. If you do not mention it, then the system capacity will be infinite. That means irrespective of the number of servers, maximum queue capacity will be infinite. Many of the cases, we will consider only these three terms, MM1, MG1, MD1, DM1. But there are cases where actually we will be considering a finite system capacity. Under those circumstances, we can have something like this. MM1K, we have a single server Markovian queuing system where system capacity is K. We will be considering small m slash small m. This is a very interesting queuing system in the sense that, okay, this M and C actually we will be using interchangeably. They represent the number of servers. Here, the system capacity is equal to the number of servers. So it reveals two things. One is there is no queue. So no customer ever will be waiting in queue to get the service. If a customer finds that all the servers are busy, the customer will leave the system. Can you give an example of such a system where there is no queue, we have multiple servers and arriving customers, potential customers. Most of the cases, certain guarantee we will find at least one server is free. But if there is no, then the customer will leave the system. Anyone can give an example of such a system where there is no queues and the system capacity is equal to the number of servers available. We use such a system in our day-to-day life, every day, every single moment. Not every single moment, most of the during a daytime we use such a system many times. Many times. Okay, just a minute. Okay, sorry for the interruption. I was asking a question. Anybody has the answer to that question? Actually, the very widely used and our day-to-day life partner telephone system is such a system. In a telephone system, you can consider a channel as a server, and the system can support as many customers as the number of channels available simultaneously. If there is more customers than the number of channels, then the customer actually is blocked. And I think you already have experienced the analysis of such a system in an earlier course, data communications, data and telecommunications, where you learned the R-long-B formula. You use this one actually without knowing the internal system. How internal? No, you knew the internal system, but you did not know how it is calculated. And this R-long-B formula actually gives you the probability of a blocking calls. And based on this probability, with a certain value of the probability, say a blocking call block rate 10%, that means blocking probability is 0.1, you can determine the number of channels that is required for a particular telephone stations or a base stations, knowing the arrival rate of the customers and the service time of the customers. So this R-long-B formula, here in this course, actually, we will be deriving the formula for this, for calculating the call blocking rate and probability of a blocked call. So symbols that are widely used for a queuing systems are these are, I already mentioned, I will skip this one here. All the examples are based on MM1, but you can have other variables like D. This indicates a deterministic distribution for the service time or the inter-arrival times. Then you have G, as I mentioned. ZI sometimes is used. This calls, it has a general distributions and the inter-arrival times are independent as well. Then some others are also there, E or something like this, but most of the cases, this M, Z, D are widely used. Now, let us consider some common queuing systems that we will be studying here. The first one, obviously, is the MM1. We will get started with this one, MM1, a single server queuing system where the arrival pattern is Poisson and the service time is exponential. And waiting customers, arriving customers wait in the queue if the server is busy. Then you can consider a slight variation of this one as MM1K. That there are at most K-1 space in the queue. You can also consider MM infinity. There are infinite servers. Whenever a customer will arrive, the customer will find one server is free. So we have a queuing system with infinite capacity. You can have small m or MMC, where there are M servers, but still the queuing capacity is infinite. As I mentioned, you can have MM. And there are MZ1. You can have MD1. You can have many other possibilities. For example, MZ5, 100, something like this. So all are meaningful, but our study will not go there. We will be focusing up to this one primarily. Then actually we will study this MG1. MG1 actually very widely used queuing system. In many cases, you will find that the service time actually is not exponential. And when you can assume that the arrival pattern is Poisson with infinite capacity, but service time actually depends on the real system. It is not possible that all the systems have exponential service times. That's why MG1 is a very common queuing system. Now, we will study a special formula, a special rule known as the Little's formula. The latest formula actually it connects the variables that we will study here. Especially if we consider the variables are the mean number of customers in the system, mean arrival rate, mean system time, then actually it is the job of the latest formula or the relation that we have that can actually connect these two variables. The mean number of customers in the system and the mean system time. Definitely a close one is mean number in the queue and the waiting time. So in our steady state analysis, what we will do, we will actually, most of the cases, find the mean number in the system. As we have seen in the last class yesterday, day before yesterday, that for a birth and death process, we can calculate the steady state probabilities of Pn. N is greater than equal to 0. So if you have these probabilities or the PMF of the number of customers in the system, then you can easily calculate the expected value of, let's say, N, as we mentioned in the last class, that N equal to 0 to infinity N times Pn. So you can easily calculate, but in many cases, the mathematical formulation or derivations are sometimes very tricky, but we can calculate it. So once we can calculate the expected number of customers in the systems, the little formula, Littlest rule, actually facilitates to know the mean system time. And if you recall that these two are the important variables, because if you can calculate the mean system time, since the service time distribution is available, you can calculate the mean waiting time. Once you calculate the mean waiting time, again, applying the latest formula, you can calculate the mean number of customers in the queue. So the random variables that we have considered here, how many? The random variables, 6. Actually, we calculate one and then actually apply the latest formula to calculate the other one. And by this way, most of the cases actually calculating the mean number of customers in the system, this N facilitates to calculate the others. So our primary focus will be to understand how can we calculate mean number of customers in the system, and we will apply the latest rule to get to the get others. So this little formula, actually we will not derive it. In your text you will find the just result. This interconnects these three quantities. If we define mean number of customer in the system is as n bar, mean system time as t bar, and the mean arrival rate as lambda, the little formula simply says n equal to n lambda. Sorry, n equal to lambda t. So mean number of customers in the system actually is proportional to the mean service time, mean system time. When the system time increases, number of waiting customers will also be. And these two are interconnected by the average arrival rate. If customers arrive at a higher rate, we will find more customers are joining in the queue. On the other hand, if the arrival rate and service rates are not actually well set, if the ratio of arrival rate and service rate approaches to 1, then actually you will find that the system actually is overwhelmed with waiting customers and queue size even becomes, in principle at least, infinity. So let's see, this is the equation that the mean number of customers in the system is actually the product of the average arrival rate and the average system time. A derivation of this one is not available in your book, and we will not go for the detailed derivation. Rather, we will actually understand this rule from an intuitive perspective. Let's see how can we define this relation intuitively. We'll consider this diagram. The x-axis of the diagram shows the time parameter, and the y-axis shows the number of customers in the system. You can see two staircase lines here. First one represents alpha t, is the number of customers that arrived in the system by time t. So we can say number of arrivals by t, or during the starting time and t, not including t. Okay. And you can see the first customer arrives here at time unit 1. So we have first customer. At time unit 2, 3, we have the arrival of the second customer. At time unit 4, we have the arrival of the third customer, and so on. We have a variable delta t, which represents the number of departures by t. For example, the first customer departed, if we consider the right side axis as the departed number of departed customer, then the first customer departed at time 4. The second customer departed at time 5. And the third customer departed at time 6. So if we consider up to time unit 6, then all the 3 arriving customers, the first customer arrived at time 1, second at 3, third at 4, actually completed their service by time C. And when both the two graphs touches each other, actually at the time, there is no customer in the system. On the other hand, the vertical gap between the two curves represents the number of customers in the system. For example, from time unit 1 to 3, we have only one customer in the system who is receiving his or her services, and so the customers in the system is 1. At time unit 3, we have the arrival of the second customer, and the gap between the two curves shows there are 2 customers in the system. Now, at time unit 4, the first customer depart here, and the gap reduces from 2 to 1, and we have one customer in the system, which is the second customer who is receiving his or her service. So the vertical gap between the curves indicates the number of customers, in the system at time t. Another thing is that another important quantity is area between two curves. If we consider the area between two curves for this part of the graph from time unit 1 to 3, this area equal is 2 units. This indicates for these 2 unit of times, there is only one customer in the system. So this unit can be represented as 2 customer time. If we further consider it, then the gap between the vertical lines here, for example, as I mentioned, the gap between the horizontal lines of horizontal curve, horizontal difference between, vertical difference between alpha t and delta t represent the number of customers. Similarly, the horizontal difference between delta t and alpha t represents. Can anyone tell what is this horizontal gap represents?
Sir, the service time.
Service time. Okay, very good. Then let us consider the second one. Here, the customers 2 arrives at time unit 3 here. That's why the number of customer is 2. Since customer 1 is still continuing his or her service up to time unit 4, so so we can divide this second horizontal arrow into 2 parts. One is this one, another one is this one. The first unit, this one actually is the waiting time of customer 2, right? Because the server is busy, server is occupied by customer 1. And the second part, this one represents the service time. So as you mentioned that it is the waiting time or service time. You mentioned it is the service time, but it is actually both the service time and the waiting time. So the horizontal gap between the curves alpha t and delta t, or sorry, more specifically the delta t and alpha t, is the system time. But it is not the gap between delta t minus, because delta t actually is not represented by that. You need a reverse function that for this delta t you need to get the time x-axis function. So we do not consider, just for understanding, the horizontal gap actually between the curves delta t and alpha t represent the system time of each of the customers. And the system time, as we know, is the sum of the waiting time and the service time. Some cases, the waiting time can be 0. If an arriving customer finds the system is idle. Now, if each of the horizontal rectangles represent the service time, system time of the customers, then what does area between 2 curves represent? Is the question clear?
The total system time.
The total system times of all customers. And from here, we can derive 2 quantities. What are the quantities? We can define one thing that we call, if we take the ratio of alpha t and t, if we divide alpha t by t, then we actually get one quantity. What is it? Alpha t says number of variables up to time t, and if we divide it by t, then it says average number of arrival per unit time. And we can actually consider it the average arrival rate. This quantity is average arrival rate, and we can denote it by lambda t. T is the arrival rate at up to time t, or during the interval 0 to t. So this quantity lambda t representing the average arrival rate up to time t, or during the time 0 to t for this system. This is one quantity of interest. Another one is if we divide, okay, if the total system time of all customers, if let's say these areas of these horizontal time units is denoted by gamma, then the total system time up to t is represented by gamma t. Total system time of all customers is represented by. Now let us define this quantity. Gamma t is divided by alpha t. What do we get? This gamma t represents the total amount of time spent in the system by all customers, and alpha t represents the total number of customers. Then actually we get the average time spent, average amount of time spent in the system by a customer. So we can consider it as the average system time. So these two variables actually now are very important one. One is the average arrival rate. Another one is average system time. Now, if we actually want to find out the third quantity of interest, that is average number of customer in the system at time t, at any time t. Then by processing these two formula, we can consider that it is, what is the average number of customer in the system at time t?
So total number of customers divided by the service time, total service time.
Okay. So this quantity actually, this average number of customer in the system, usually this is not system time, the system time is this one. We call this quantity as a job average quantity. Job average? No, this is not job average. Job average quantity is another one is time average. Those who have completed the simulation course, I think they know the difference between the job average and time average quantity. In case of the job average, actually what happens? We have some items with some specified values. For example, a person can have his height. So we have a number of items with some quantities associated with this item. Then if we want to know the average amount of quantity per person, then what we do, we just sum up all the quantities and divide it by the number of items. This is what actually usually we call the arithmetic average. However, when we want to calculate time average quantity, then what happens? Over times, the quantity is changing. For example, if we focus here, the number of customers in the system up to this point, it is 1. When we move to time unit 4, it becomes 2. Not big. No, sorry. Up to 3, but not including 3, it is 1. At 3, it is 2. But when we reach at 4, then actually one customer depart. Now the number of customer again becomes 1. Then at time unit 4, one arrival occurs. Then actually the number of customers, no. time unit 4, one arrival occurs, one customer arrives, and we have the number of customers 2. Just before 5, it remains 2, but when at time 5, the second customer depart here, the number of customer becomes 1. So the time average quantity actually defines the average number of customers over time, over a particular time unit. Then actually, if we divide the total system time of all customer, with the unit customer time, and we divide it by the total time, then actually it number of customers per unit time remains. So the total customer times over a period is divided by the total time. Then actually we find the number of customers per unit time. For example, here if we consider, okay, let us draw this diagram here. Ready? We want to consider this one from time unit 1 to 6. How many time units here? 5. Out of this time unit, if we consider here the first 2 time unit, we have 1 customer. And then from 3 to 4, we have 2 customers. Let's say up to 3, here we have 1 customer. We have 1 additional customer here. Then from 4 to 5, we have 1 more customer. Then instead of considering this one, let us now see it other way around. Not this color, blue is good. This rectangle says 1 customer from 1 to 4. So you have 1 to 4, 1 customer. This rectangle says another 1 customer, of which here from 2 to 3, 1, and 3 to 4 to 5, 1. So you can have this one. Now, if we put these 2 rectangles side by side, we can find from 1 to 6, 1 to 5, actually 1 customers all the times. And out of this rectangle, if we put 1 rectangle here, then we have 1 customer throughout the time 1 to 6 per 5 unit. Then we can say at least 1 customer is there, but this additional one that we could not fit here can be placed here during this time for 5 unit of time with an average value of 0.2 throughout this system. So we will have 1.2 customers on an average per unit time. So ultimate thing is that if we divide this total system time of all customer by the total time, then we get the average number of customers in the system over time. And this is actually this gamma t is divided by t. And now combining these 3 equations, what we will get from this immediate above equation, we can replace gamma t by alpha t times t sub t. And from this equation, we can replace t by alpha t by lambda t. So we have alpha t here, and by lambda t, we can write the lambda t here. Now this alpha t and alpha t cancel out each other. So what we have, the average number of customer in the system at time t is simply lambda t times t. All of these quantities actually are averages. That's why you can have the bar here. So when t becomes infinity, then we can write this equation in this way. N bar is equal to lambda times t bar. So this is the Little's formula, widely used Little's formula, Little's rule, that actually interconnect this job average quantity and time average quantity by the arrival time, average arrival time. Already one, right? Sorry, just I will take few more minutes before finishing this one. I am a bit slow today. So we started late actually due to actually I started late. So I will take 5 to 7 minutes so that the students who are residing in the hall or was home will not miss the Johor prayer. Now we will be actually formulating this MM1 queuing system. I will take 5 minutes. So in this MM1 queuing system, what we do, customer arrives at a position following a position process with rate lambda, irrespective of the number of customers available in the system. The birth and death process that we analyzed in the last class had lambda 0 here, lambda 1 here, lambda 2 here. So in that case, the arrival rate depends on the number of customers in the system. Also, the departure rate depends on the number of customers in the system. But for this MM1 queuing system, our assumptions are the arrival rate and the service rate will be fixed irrespective of the number of customers in the system. That's why what we can say, that lambda n is equal to lambda for n greater than equal to 1, and mu n is equal to mu for n greater than or equal to 0. So this is our one assumption. And second thing is that we have infinite capacity, but there is a single server. Those who can recall the last class can recall these equations. The first one is the probability that in the steady state there will be 0 customer in the system is 1 over 1 plus this one. We derived this equation in the last class rigorously. So we'll not consider this one in detail here. And the second thing is that the number of probability that the number of customer is n in the system is simply this probability multiplied by P naught. So P naught is 1 over this one. So this one comes here. Now, if we simplify this equation a bit with the assumption that the rates are unique, lambda, arrival rate, irrespective of the number of customers in the system, and the service rate is also same. Then actually all these lambdas here becomes lambda, lambda, lambda up to lambda. How many lambdas will be there? From n. If n equal to 1, then there will be 1 lambda. If n equal to n, then there will be n lambda. And in the denominator, we will have mu, mu, and mu. How many mu's will be there? Exactly n mu's. Then this part of the equation, P naught, can be written n equal to 1 to infinity lambda by mu to the power n. So there will be n lambda, that means lambda to n. There will be n mu, that is mu to n. We can combine this together. There will be lambda by mu to n. And the equation for P naught will be P naught times lambda by mu to the power n, and if we assume that this lambda by mu actually is represented by a quantity, we call it rho, usually represent the traffic intensity in the queuing system, then lambda by mu equal to represent by rho. Finally, how can we represent this summation? So if we simplify this one, the simplification I'll show you in the next class because I want to finish it on Lady 10 107. I'll finish it here. with one equation that if I will write before going to, okay. The derivation will be shown in the next class, though here we can write this one equal to 1 minus rho, and then this equation Pn becomes 1 minus rho times rho to the power n. So this is the probability that there are n customers in the system. When n equal to 0, then this becomes 1 minus rho, and when n has a value, then this becomes 1 minus rho times rho to the power n. Using this equation, we can calculate the expected number of customers in the system, which will be for n equal to 0 to infinity n times P n. And this will result in something. We will discuss this one in the next class. For now, we will finish here section 125. And if you have any question, we can continue. Otherwise, we can finish the class. Any questions? Okay, thank you very much.